Welcome back to the second part of chapter 6. We are still discussing this part of logic circuits, latches, flip-flops, and timers. And we said in the first part that we are discussing a new type of logic circuits where we have a feedback from the output back to the input. And that's why these circuits are not quite similar to the circuits we addressed before. We have a feedback from the output to the input, and that creates a new rhythm or a new style of logic circuits. So we discussed the idea of latches, we discussed the idea of flip-flops. We are still discussing flip-flops. This is the part that we will cover the rest of flip-flops, and I will see if it is long. I will divide it into two other parts, so we may have like second part and third part. Anyway, let's just carry on and see how it goes. We are still having like topics to cover in flip-flops, and we explained about D flip-flops, JK flip-flops, their concepts and how they work. Now, for some reason, we may have something we call a synchronous preset and clear inputs. Asynchronous means what? It's not synchronized with the clock cycle. It's relevant to the operational process of the flip-flop. However, it affects its output. Meaning what? I can control the output of the flip-flop regardless of its own clock or the operational clock of that flip-flop. Okay, so in that case, we do not have a synchronization, and that's why we call it synchronous. We can change the output based on another input somewhere else, not the clock or JK, or JK. So because these are also contributors to the output, as we explained before. Now, these two inputs may control the output based on their activation. If it is active high or active low, let's say like in this case active high, this is the preset. Okay, that means if this one is active, Q will be high no matter what. So we wouldn't care about whatever available here. Clock cycle, rising edge, falling edge, J and K, it doesn't matter. It's just will be set, or the output of the flip-flop will be set no matter what. And the same goes to clear. If it is active, in this case, like if it is low, because this is active low, then the output will be low no matter what. The clock cycle, the rising edge, the falling edge, it doesn't matter. Here we have the rising edge, J and K, regardless of their values. So this is clear, CLR, active low, that means CLR bar, and pre, that means preset or direct set. Sometimes we refer to it by direct reset, okay, RD. So don't be surprised, okay, and direct set. I'm sorry, clear is direct reset. I'm very sorry. For the pre, that means preset, it's direct set, SD. So don't be surprised if you find SD, that means it's direct set, or preset, it means the same. That means it sets the output Q to high. Of course, Q bar is the opposite or the invert or the inverse of Q, and that's why we have a synchronous activation here. We don't care about J and K and the clock cycle. All right, so let's just go and take an example, not to extend any discussion. Let's say we have a D flip-flop. Now we don't have the operational process of J and K, so it would be Q would be D based on the rising edge here. Why rising? We don't, because it's active high, so it goes with the rising edge. Active high, that means we don't have an inversion here. We don't have the bubble that states that C should be low or active. Actually, active while at the falling edge. I can't say low at the falling edge because this is like edge triggered. It's not a level triggered. All right, let's read the example for the positive edge. Again, as I said, edge triggered D flip-flop with preset and clear. Preset and clear, and pay attention, they are active low. That means they will be activated when they are low. Okay, inputs shown below, determine the Q output for the given inputs if Q is initially low. And as we agreed in the previous session, we studied, this is pointer, I'm sorry, this is pointer, what did I take? I need the pen, not the pointer. Yes, the pen. All right, so as we agreed in the previous session, we said that the question should tell you what is the initial state. That means what's the initial Q, because you can't just guess. If it doesn't give it to you, it's up to you to assume it low or high, but just state. Let's say for some reason, usually we do give the initial state of Q. Or let's say for some reason you don't find it in the question, or you don't have any indication about it, then you can assume it. In 90% of cases we assume it low, but it's up to you. If you assume it high, just say I'm assuming Q is high, or assuming that Q is initially high. Okay, now it is given, it's low, so you don't have to assume anything, you start low. Okay, you start low. Now look, we have the clock cycle, the rising edges. At the rising edges we have the change, but we are not quite sure how it will happen. Why? Because we have preset and we have clear. Now let's check the preset. If it is high, it won't change anything. Why? High, it's active low. Now it is high, okay, it won't change anything. Also clear is high, okay. So until, now look, we have a change in the preset here from high to low, this part, okay. Means we will ignore all these pulses. They don't matter to us. They won't change anything. Initially Q is low, okay, it will just go low. Now here we have a preset, right, at this edge here, at this timing line. So it will go high no matter what, okay, until here. Now this one deactivated, that means it went up high again, okay. So now Q will not change unless there is something that changes it. Okay, our preset goes active high, goes high while it is active low. That means it's not activating anything. Now Q initially is high. It will carry on high as long as these two are high. Now as you see, they are both high. Now we will go to normal operational process. Normal operational process, we will look for the first rising edge. This is the first rising edge. Okay, now here, the first rising edge, we don't care about pre and clear, why they are high, they will not affect anything. Now look at D. What's D here? Now look, it's low, that means Q will be low, it will follow D. So up until here will be high, then it will drop down to low. Okay, now these two are still high until when? Until here, look at this part, it changes, one of them changes from high to low, which is clear. Okay, until then we will just carry on solving based on the operational process of the flip-flop itself. Alright, the next rising edge, this is the next rising edge. Okay, for the next rising edge, what we have, now look, D is high, and this is the next rising edge, so it will carry on low until the next rising edge. It will go high based on D. Okay, high until the next rising edge, it will not change because we don't have anything to change it here. Okay, the next rising edge, high. Now look, D is low. Here, at the rising edge, it will go low until the next rising edge. Okay, until the next rising edge, it will carry on low until the next rising edge. The next rising edge, what will happen? We have here high for D, it will go high. Okay, and then now look, we will not go until the next rising edge. Why? Because there is here clear at this point. We have clear, so it will be forced to low no matter what, as long as it is low. That's why we call this one clear and preset asynchronous. If they are activated or if they are active, then the operational process would be disregarded. We will just take their own operational process. Okay, here the flip-flop will be reset, set, reset, set. Here will be clear or direct reset, or here will be preset, or actually direct set using this pre. Okay, that's how you solve this question or this type of question. Pay attention to this. I always explain about this type of, this period is very important. Now, after the preset or the direct set, what you need to do, you don't say Q will go low by when it's on. It will not. Q won't change unless there is something forces it to be changed. So if we have it high here, it won't change unless I have a rising edge. Why? Because this is active at the rising edge. Or there is a change in pre or clear. Now, as you see, we don't have, usually, this is not the case, we don't have pre and clear low at the same time. Why? Because the flip-flop will not know exactly what to do. Should I force Q to high or low? And that would be confusing. Ultimately, one of them will go before the other, depending on the delay in the circuit itself or this chip. But we are not quite sure. We won't be. There is no way that you can guarantee pre will be before clear or clear will be before pre. In that case, you will not be sure what will be the output. That's why we don't have both of them at the same time low. Actually, it means nothing. You are trying to that means you are trying to set and reset the flip-flop at the same time. It means nothing in electronics in this regard or in this sense. Okay. That's how we solve this kind of examples. All right, let's carry on. Now, one of the applications widely used or widely developed using flip-flops is the frequency division. Frequency division means what? Now we have signals. These signals have period, and of course, if they are periodic. Okay, if we speak about a clock is periodic. Means like something like this. Look, this one. Periodic means this one. Now look, this pulse repeats itself after a certain period. Now this one is a period here. Okay, so it repeats itself again, repeats itself again, again. This clock is, of course, periodic. It has a frequency. Frequency, that means the reciprocal of this time here, as we explained before. So we take the time here between these 2 points, tau or t, and then we take its reciprocal 1 over t, means the frequency of this clock. In some applications, we may need to either increase or decrease the frequency. Okay, so in order for us to do that, we can use flip-flops. So they may reduce the frequency for us. Okay, and reducing the frequency, in that case, we can either divide the frequency by 2 or by 4 or by whatever the number that you want. And in that case, we can have some common application actually for frequency division using JK or actually D flip-flop, both of them. Now let me give you the common design or the common configuration of the frequency divisor or the frequency, a circuit that achieves frequency division by flip-flops. We will go through both of these. Now look, for D, we take the Q bar, or actually the inversion of Q, the second output of the flip-flop, we feed it back to D. Now we don't have any input other than the clock. Now the clock, just the synchronization clock, is the input. Why? Because we are interested in dividing its frequency. Okay, dividing its frequency, that means a little bit expanding its time. In this case, we will expand its time period by 2 or multiply it by 2. How? I will show you. Now, when we feed this Q bar to D, what will happen? Now look, assume that initially we have Q as 0, okay? Just 0 or low or reset the flip-flop. Now at the rising edge of the clock cycle, what will happen? The flip-flop will be set. It won't change until we go to the next rising edge. right? So we would wait until the next rising edge. Now we will check what is D. Now we said initially it was set, okay? So this one is reset. So initially set, of course this one is reset, fed back, that means this one will be reset for again one cycle. Then this one will be reset and this one the opposite. It will be set. So it is exactly expanding or actually dividing the frequency of this by 2, expanding the time by 2. Okay? So the whole pulse here, the whole period will go set, the other one will go reset, set, reset. We are multiplying the time by 2 here and dividing the frequency by 2 in this case. Now the same goes to JK. JK, we connect both of them to high, or this is like 5 volt, or maybe it depends on the chip, but let's say high, that means just active in this case all the time. And what will happen? It's toggle, right? When you activate J and K at the same time, the flip-flop will toggle. If it is initially low, what will happen? This one is easier than this. Okay? So Q is initially low. What will happen? It will toggle with the first rising edge. Look at the first rising edge. Let's say if it is low now, it will toggle. That means low will become high. It will go until the next rising edge. It will toggle again, low, toggle, high, low. So that's exactly dividing the frequency. If you want to divide the frequency by 2, only 2, that means you need one stage, like this. Just one here, or here, one stage. If you want to divide the frequency by 4, you need to add another one, another stage. So you will have 2 to power n, depending on the time of the type of the frequency that you are going to divide. So if you feed the output to the clock, now here's I forgot to say. Now the second one. Now look, for the high, we don't change it because we need the flip-flop to toggle all the time. Now our clock for the next stage or the next level of division would be the Q of the first one. Okay, why? Because we are interested in dividing the output here. We have already achieved a division of the clock. We are interested in achieving a division for the second clock. Okay, that's what we are looking for here. So all of them will be connected to high. Usually we do like this. We connect both of them to the same point here. And let's say like this, just one high here. Okay, like you can just type it H or high or whatever. So this is usually the case. Now you're dividing for the first stage, or QA is dividing the clock by 2. Then the next one, QB, is dividing QA by 2. That means expanding the time. Now look, this is the first rising edge. It will be all the way until the next rising edge, high, all the way until the next rising edge, low, and so on. So if you look here, if you consider this one 1, this one will be 4. Why? This is 2, this is 4. In terms of time, of course, I'm speaking about the time here. Okay, look at the time. Yeah, if this one 1, let's say 1 second, this one will be, I'm sorry, 2 twice. This one will be 4. Okay, of course, it can't be 1 second. Usually, this is much less, maybe 1 microsecond or less even. Okay. So the division. How many stages you want? It depends on the type of the division. So 2 to n means if you have 3 stages that you will divide by 8, 2 stages by 4, 1 stage that by 2, and that's it. Okay. Look at this, like the frequency out. If you get such a question develop if out waveform for the circuit below when an 8 kilohertz square wave input is applied to the clock. Now we have the frequency of the input. We know that this is divided by 2, divided by 4, divided by 8. So F out is exactly 8 divided by 8. That means 1 kilohertz. And that's exactly what we are looking for here. It doesn't need much of a trouble. Three stages, that means you divide by 2 to 3, which is 8. So you'll divide this one by 8, that will be the output frequency, okay? In order for you to draw it or plot it, this is the frequency input. QA will be double in the time. Of course, we speak about the time. Now, pay attention. This is extremely important. Frequency is lowered or reduced, but the time will be expanded. How do I know the time is expanded? Now, look. This is the high time. Look at the high time now. Twice. This is the low time. Look at the low time. It's twice. And the same goes to this. It's twice this, 4 times this. The same goes here. It's twice this, but 8 times this. Okay. Now, during the exam, if you are going to draw this one or plot it, usually we give you this. So you just use this diagram and try to make it as fit as possible. You don't have to draw it 100% correct. We are not looking for like 100% that it is exactly twice, those are all fit, but it should be clear enough for us to understand that you picked up the idea, you understand what you are writing, okay? For counting, I will keep it for, before we go to counting, this is another application of flip-flop, because I was planning to create another video. But let me finish flip-flops, then I will create another video. We can create counters using flip-flops. Now, we said about frequency dividers or frequency division using flip-flop, but we may need to create counters. Counters means what? An electronic device that counts from 0 to a certain number, okay? Usually we don't consider 0 as a number in counting, but it doesn't matter. We still need it here in our counting. And this kind of application helps us to achieve certain number of counting depending on these stages or the number of flip-flops. Now, the elementary way to do that, we can use JK flip-flop, and again the JK are connected to high means what? Both of these two flip-flops are toggling, they are in the toggle mode. That means if the initial state is low at the rising edge or the falling edge, now look, rising or falling edge, they will be high or low based on the previous state. So they will just toggle. Now look, we have the low, the falling edge. In this case, the change of the state is exactly at the falling edge. Now look, in order for us to count, we need two outputs, QA and QB. That means the output, output of the first stage, and Q, or the output of the second stage as QB, and I will tell you why we need that. Now remember, there is not much of change for JK. Connect them to high, there is nothing much to do about them, but clock for the first one. The next clock is connected to Q. Remember, these clocks are active at the falling edge. That means they have this bubble of inversion in this case. All right, now look, let's try to analyze based on the clock cycle. Now for QA is pretty simple actually. Now for the falling, we don't have anything for the rising edge until the falling edge. At the falling edge, we assume that both of them are reset at the beginning. Just assume. Okay, at the falling edge, what will happen? Initially, the QA is 0. The flip-flop is at the toggle mode. At the falling edge, okay, pay attention, the falling edge. The flip-flop, the first one, QA, will be set. Okay, so this is what we are going to have, set. Okay, now look, how about QB? Will it be set? It will not be. Why? Now, QA is the clock for the next flip-flop. Now, look, the rising edge here will trigger this flip-flop. It will produce output, yes, but this will take time. Even like 1 picosecond or less, it will take time, maybe a fraction of a picosecond, but it will take time. Means, until we get our output here, this one will not be triggered immediately. Now look at this. Okay, we have rising edge 1. Okay, it will trigger at the falling edge. When will happen the falling edge? The next clock falling edge. So the first one will not affect this. We are taking a rising edge. So nothing will change here. We don't have any falling edge. We have a rising edge fed to the second stage flip-flop or flip-flop B. Okay, so B will be reset again until the falling edge here, which comes by the second clock. Now look, this one is set after the first falling edge of clock set. Okay, so the flip-flop is toggle with the next falling edge. It will be reset. Good. Reset. This is a falling edge, which is an input to the next stage. It will trigger this flip-flop, which is at the toggle mode also. We will create what? Change in the state of QB. QB is initially 0. So it will be changed from reset to set. The same process will be repeated. 0, 1, 0, 1. Here 0, 0, 1, 1, 0, 0, 1, 1. Now let's count. Count from B to QB to QA. That means from B to A. 0, 0, 0, 1, 1, 0, 1, 1. So this one will be, this flip-flop design will be able to count, or it will enable you to count until 3. 0, 1, 2, 3. So what do we have? 1, 2, 3, 4, 4. That means 4 decimal numbers, which is actually 2 to power 2. Why? We have 1, 2 flip-flops. So 2 to power n, and here 2 stages. That means you can count up until 4. 4 in decimal. So 0, 0, 0, 1, 1, 0, 1, 1. Then after this process, the thing will be repeated again. How do I know until 4 it will be repeated? Now count 1, 2, 3, 4, 4 pulses, 4 clock pulses for the first input. That is exactly 4 in decimal. That's exactly what we count. Then next to that, it will repeat the process. There will be nothing else to be done. It will go 0, 0, then 0, 1, 1, 0, 1, 1. Again, it will repeat the same process over and over again. So this is the simplest way for creating a counter using flip-flops. Okay, take an example. Determine the output waveforms in relation to the clock for QA, QB, and QC. Now look, we have three stages. That means 2 to 3, which is 8. Meaning we will count from 0 to 8. From 0 to 7. 8 numbers, okay, from 0 to 7. Okay, now, as I said, if you are not given the state, assume QA, QB, QC are initially all reset. And then look at high is connected to J and K. Then all of these flip-flops in the toggle mode. Now look at QA is connected to QC, is connected to the clock of B. QB is connected to the clock of C. I mean the third flip-flop. Now look at this. We have an inverted, or actually the falling edge activation. So this is a counter. Because I usually receive this question, or I get this question, students usually ask me, what's the difference between frequency divisor like this and the counter? Actually, they do almost pretty much the same, but one of them is we need to go from 0 to 1, 2, 3. Here we have already actually 3, then 2, then 1, then 0. It's like backward counter. It's a backward counter. Now look, this is 1, 1, right? High, high, 1, 1, 1, 0. This is 3. 1, 1 is 3. 1, 0 is 2. 0, 1 is 1, 0, 0 is 0. So it's a backward counter. That's the frequency divisor in this case. That's why we invert the clock. And when we invert the clock here, what will happen? We will activate when at the falling edge, and that will go from 0, 0, 0, 1, 1, 0, 1, 1, opposite to this, not backwards. Okay? So that was an important point to highlight. But in this case, we have already the bubble, we have the inversion, that means at the falling edge. So we have a forward counter. Forward, that means we go from 0 to 1, 2, 3, 4, 5, 6, 7. 7, why? Because 2 to 3, that means 8, we count from 0 to 7. 0 to 7 means 8 decimal numbers. Okay? Now look at this. We can have this clock. Now remember, from 0 to 7, that means 3 digits, as I said, a digit for each of those, 0, 0, 0 to 1, 1, 1. Okay, 7 is 1, 1, 1, right? Okay. So now, the clock cycle, nothing will happen. All of them are zeros until the first falling edge of the clock. At the first falling edge of the clock, QA will be set. None of QB and QC will be set. Why? Still until the next falling edge. The next falling edge here. Both of these will change. Now, this one will go to 0. So it will be 0, 1, 0, 1, 0, 1, exactly like in the truth table for the last. Usually we have like 0, 0, 0, 0, then 1, 1, 1, 1 for the first, right? Then for the second we have 0, 0, 1, 1, 0, 0, 1, 1. Then this one we have the last one 0, 1, 0, 1, 0, 1. This is exactly as a counter. Why? Because we're counting like this. We have the most significant bit, the least significant bit. So the first falling edge, QA will change. Why it will change now? Look, clock, first falling edge. The flip-flop A, this flip-flop A, will change based on this clock. So it is high, that means it will toggle. Assume that initially it's at 0. So it will be set. It will not change. None of these will change. Why? Because it will change at the falling edge. The falling edge of what? QA. Now look, QA has just begun going high. That means we will wait until this one goes low. Okay, good. So this one will not change. This one will not change. It will remain the way it is. Now let's address QA at the next falling edge. It won't change until the next falling edge. At the next falling edge, it's toggle, so it will go from 0 to 1. Good, we have a falling edge. So this falling edge will affect QB. So at this time, QB initially is 0. It will be high. Why? It will toggle. Okay? So it will go on high until not this edge. This is rising edge. Remember, this is rising edge going from 0 to 1. It will not change until the next falling edge from 1 to 0. So from 1 to 0, we have falling edge. This one will affect, this is the first falling edge of QB. It will affect C. This is C, this is B. So QC will start going high here. Why? It is toggle. So initially 0, it will go to 1. And we'll go on until the next falling edge. The next falling edge is exactly the repetition of this. 0, 0, 1, 1 is doubling this. Okay? And that is how the count happens. 0, 0, 0, 0, 0, 0, 0, 1 until 1, 1, 1, 1. Then it will repeat the same process. Okay? All right, timers. I'll create another part. Until then, have a good time. Goodbye.